now, what I am going to do is I am going to give you a second algorithm to solve the same problem, and this second algorithm is going to be called iterative policy evaluation. And the reason I am giving you this algorithm, because it will build towards what I want to get to, which is the value iteration algorithm. So, same problem, I have also computed value of goal to be 0, value of S1 to be 1 in this case, but I have a problem in computing value of S0 and value of S2. I know that value of S2 is determined by 3.7 plus 0.3 times V pi of S0. I know that value of S0 is determined by 4.4 plus 0.4 times V pi of S2. You can check these numbers. Right. Now, a simple way to do this is that I randomly initialize these values. So, I just say S0 is the goal, it has value 0. But if I know S0, then can I compute S2 using this second equation 3.7 plus 0.3 times this. So, what is my new value for S2? What is my new value for S2? 3.7. Now, something happened. S2 has new value, its value is 3.7. So, that changes the value of S0. What is the new value of S0? Something 4.4 plus 0.4 times 3.7, which is 5.88. Now, S2 says, dude, you changed your value, now I have to change my value. So, I change my value to 5.464. Same thing happens with S0, it says no, my successor has changed its value, I am going to change mine. So, it becomes 6.58, then S2 says the same thing, it becomes 5.67, it says the same thing, it becomes 6.67, it changes, it keeps on going. What do you observe? That at least for this tiny example, they seem to be converging. And in fact, you can prove that they will converge under some assumptions which we are not going to talk about. The assumption is that everything should be well formed, every value function should be well formed, and what does that mean? We will leave it to an advanced course. This algorithm is going to be called iterative policy evaluation. It basically says that if I want to compute the system of equations which are given in this box, I will randomly initialize them and approximate them by V pi of 0. And in fact, if I am given an approximation V pi n minus 1, which is n minus 1th approximation for the V pi function, then in the right hand side I will use the previous approximation and I will compute the new approximation V pi n, and this n sort of denotes the number of approximation. Just to clarify, it is the same equation, but on the right hand side I use the n minus 1th approximation, on the left hand side I compute the nth approximation, and this algorithm would be called the iterative refinement version of computing the system of equations. You can call it iterative policy evaluation. So, this is it. So, this is your pseudo code. Let us work with this together, so that we are in it, we understand this. So, there is one assumption which I was trying to hide under the rug, but I will just quickly say the assumption is that your policy pi is proper. Proper means that eventually you will reach the goal with from every state. If that does not happen, think about what happens. So, with 0.2 probability I do not reach the goal starting in state S, then what happens? Its V pi becomes infinite. Its V pi becomes infinite, because it becomes 0.2 times infinity plus 0.8 times some finite cost, and that we do not like. So, we will assume that my policy pi is proper. That means that from every state I will finally reach the goal. I do not know in how many steps, but I will finally reach the goal in definite horizon. So, in that assumption this algorithm works. It basically says you can initialize V0 pi arbitrarily, finitely. Just don't do infinity minus infinity. You can do it all zeros, all 2's, all 55, all some 1, some minus 1, some 35, some minus 35. It does not matter. The algorithm is so robust that you can give it any initialization and it will work. Make sure the goals are 0. Don't mess with the goals. So, value of goal is 0, everything else you can initialize as you want. Then what you do is you repeat the following steps. In every iteration n, for every state you use, so this is iteration n, for every state you compute the new approximation using the equation that we described earlier in the last slide. So, here I will be using the n minus 1th approximation and I will be computing the nth approximation. Now, when I do this, I maintain a previous set of values and I maintain the new set of values. Such an algorithm is called, does somebody know what kind of an algorithm it is? It is a dynamic programming algorithm. Very good. Now, you will think about where is the repeated computation and so on. I will let you think about it. So, it is a dynamic programming algorithm. Now, the problem is that I need to stop at some point, and my notion of stopping should be that my values have converged. What do you mean by values converged in this case? So, what do we want? We want the nth approximation to be very close to the n minus 1th approximation for every state, not just for me, but for every state. In fact, think about it. If it is not true for every state, if it is not true even for one state, then it is possible that its predecessor will suddenly change its value in the next iteration significantly. So, we want this to happen for every state. So, we will also compute a phenomenon called residual. Residual basically says what is the magnitude of the difference between V pi of n minus V pi of n minus 1. Here I am computing residual for every state, but then I will say that you will stop when your max residual is less than epsilon, and such a value function will be called the epsilon consistent value function. It is not the optimal value function, it is epsilon close to the optimal, and you can actually have a bound on how close you are if you have a epsilon consistency. We will not talk about the bound for now, but it is close, and this is my termination condition, and you return the value function V pi n, which was the question at hand. How do we compute the value of a policy? And moreover, you can prove that for a proper policy P, a pi, iterative policy computation converges to the true value of the policy, that is limit n tends to infinity V pi of n is equal to V pi irrespective of the initialization V naught for every state S. This all only happens for a proper policy, and this happens in the limit. Question. Is there experimental and theoretical evidence on how fast it converges? And absolutely. And you can say that the number of iterations you will take will be polynomial in epsilon 1 over 1 minus gamma and s. Okay. So, you can there is a huge theory on this. Right. This model came out in the 50s. Okay. So, we are really we are really behind in our understanding of the world, right. So, after 50s lots of things have happened. Now, I want to take the leap, and the leap is we only started with a brute force algorithm, right. The brute force algorithm we started with was that you start with you enumerate all policies pi, and then you evaluate the policy of the pi and then pick the best. Now, we have solved the brute force problem, because now we know how to evaluate a given policy, but that is not sufficient for us. right, because we cannot enumerate an exponential number of policies, that is just not going to happen. So, what we will do is we will take this intuition of iterative policy evaluation and convert it into an algorithm called the value iteration algorithm, which would go beyond the brute force.